Okay, the trick to working with Atwood machines, or really with anything in this unit, is to remember that the sum of the forces equals the mass of the system times the acceleration of the system. So in other words, if I find the total force acting on the system, it's going to equal the total mass of the system times the total acceleration of the system. So that's the trick, is to think in terms of the whole system. So let's start with the first one. What is the net force acting on the system? Well, I've got 80 newtons acting this way, and I have 50 newtons acting this way, and they're acting in different directions. Now, maybe this is confusing to you, or maybe it's not. The answer is the net force is 30 newtons in this direction. But perhaps it might help you to think of it this way. We could say, well, if I take these two pulleys and I lift this one this way and this one this way, and I just make it a tug of war, well, if I had a tug of war, I'd have basically 80 newtons acting this way, and then I have the other one pulling this way. They're no longer on the pulley, and this way I've got 50 newtons. It's pretty clear in this case that the answer is I'm going to have 30 newtons of force acting in this direction. So basically, 30 newtons is the force acting on this whole system. The trick to remember is that this is acting on the system, not just on the 8 kilograms, but on the whole mass of the system. Now we're told that the string is massless, so I can ignore that. So the mass of the system is, if I want to find the acceleration, acceleration always equals the sum of the forces divided by the mass. So the sum of the forces we determined to be 30 newtons. The total mass is going to be 8 plus 5, which is 13 kilograms. 30 newtons divided by 13 kilograms gives me 2.3 meters per second squared of acceleration. Now let's talk about something here. What direction should I make this? Is this positive or negative? It's moving in a downward direction. But really, when we're working with Atwood machines, probably the best thing to do is say, or with things on inclines, is to say, let's just call the direction of motion positive. Really, in physics, we're allowed to define which direction is positive and which is negative. We often use a coordinate system and just say, right is positive and up is positive, like we did in kinematics. But in this case, it really is going to simplify our lives tremendously if we just say, hey, whatever the direction of motion of the system, that's the positive direction. So I'm going to look at this side and say, that's moving this way, that's positive 30 newtons, so therefore that's positive 2.3 meters per second squared of acceleration. Now, how does the magnitude of the acceleration of object A compare to the magnitude of acceleration of object B? Instead of doing this mathematically, let's just think about this intuitively. They're connected by a string. If this one is accelerating downwards at 2.3 meters per second squared, this one has to be accelerating upwards at 2.3 meters per second squared unless the string is stretching, and we're not told that it is. So the answer is they're accelerating the same, and that really is the trick to Atwood machines, is to remember the mass is equal to the combined masses, but the acceleration is always the same for both of them. Now, what is the net force acting on object A? You might be tempted to go, well, it's 30 newtons, but that's not really, that's the net force acting on the system, but this is not the whole system. So what we have to do here is say, well, the sum of the forces always equals mass times acceleration. Now, we're told then if we want to know what the net force acting on object A is, we just take the mass of object A, which is 8 kilograms, and we multiply it by the acceleration of object A, which is 2.3, and that gives us 18.4 newtons. So although the net force acting on the system is 30 newtons, the net force acting on object A is going to be 18.4 newtons, and it's going to be acting in a downward direction. Now the next one, what is the magnitude of tension force T1? So the way I'm going to approach it is I'm going to say, hey, look, the sum of the forces acting on the system equals mass times acceleration, which I've already calculated, but it also equals the sum of the forces. In this case, I have a downward force, which is going to be mg, and an upper force, which is T1. So in addition to equal mass times acceleration, it equals mg plus T1. So I'm just going to substitute in here. The sum of the forces calculated by finding ma is 18.4 newtons. The downward force of gravity acting on object A is 80 newtons plus T1. So if I solve this for T1, what I get is negative 61.6 newtons. Now, since we defined the downward direction of this one, the direction of motion as being positive, it makes sense for that to be a negative force. Now, the next one is F. How does the magnitude of T1 compare to the magnitude of T2? Well, if we think about it, imagine again if we straighten it. If we straighten it out, we'd see that however hard I pull in one direction is how hard I pull in the other direction. That the tension on this is always going to be the same as long as this pulley is massless. So if this one is pulling with 61.6, this one has to also be pulling with 61.6. The tensions are going to be the same. Okay, let's try here now. Number 2, the diagram shows two masses connected by a string. We'll assume that the string is massless and that the pulley is massless, and that both the pulley and the table are frictionless. Gotta love those massless, frictionless objects. So what is the net force on the system? Well, let's see. I have 80 down is mg here, but the table's pushing up with 80 that way, so those two cancel out. All that leaves me with is this. I have 5 kilograms being pulled by gravity downwards, so the mg of this is what's going to set this whole system in motion. So the net force on the system is 50 newtons. I don't see anything else that could be causing it to accelerate. What is the acceleration of the system? Well, acceleration equals the sum of the forces divided by the mass. So here's the sum of the forces, 50 newtons. And the mass of the system is not just this 5 here, but it's also this 8 here. So the total mass of the system is 13 kilograms. So the sum of the forces divided by the mass gives me 3.8 meters per second squared. And we're going to define the direction of motion as positive. How does the magnitude of acceleration of object A compare to the magnitude of the acceleration of object B? They have to be the same because they're connected by the same string that has the same tension. Now, what is the net force acting on object A? So to find that, I have to remember that the sum of the forces equals mass times acceleration. The mass is 8, the acceleration is 3.8, so 8 times 3.8 gives me, I guess I need to move this over a little bit, gives me 30.4 newtons. Let's keep going here. What is the magnitude of the tension force T1? Well, I already know that the net force acting on this on object A is 30.4 newtons, and there's only 3 forces acting on it. There is 80 newtons of gravitational force acting downwards, 80 newtons of normal force pulling upwards, and 30.4 newtons pulling this way. So the answer is 30.4 newtons. How does the tension of T1 compare to T2? It's the same string, and there's nothing in between them, so it's going to be the same. And if you're not sure, if you don't believe me, we could just try this real quick. Watch this. Let's just double check that. So what I'd have here for object B then is I would have 50 newtons of downward force minus 30.4 newtons of upward force, which would give me a net force of 50 minus 30.4, which would give me 19.6 newtons of downward force acting on 5 kilograms. If I divide that by 5, I get 3.9, and that's not exactly 3.8, but the difference has to do with how I rounded this one. This wasn't actually 3.8, it was 3.846 and so on. So I know I've done it right. Okay, so now the deal is I don't know what the mass of A is, but I know some other information. I know that mass B is 2 meters above the table, and it takes above the floor, and it takes 1.2 seconds to reach the floor. So we start off. What is the acceleration of the system? Well, I'm going to use d equals 1/2 at squared, where d is 2 meters. I'm looking for the acceleration, and the time is 1.26, so I square that. And when I solve that for A, I'll find A is 2.5 meters per second squared. Now that I know how fast the system is accelerating, I can use the sum of the forces equals mass times acceleration and find the mass of the system. So the sum of the forces on the system equals the mass of the system times the acceleration of the system. the sum of the forces, the forces acting on it, since this is a frictionless table, is just mg. I have 50 newtons pulling down. Now, I don't know what the mass of the system is, but I know it's accelerating at 2.5 meters per second. When I solve for m, I find the mass of the system equals 20 kilograms. Well, therefore, what is the mass of object A? Well, the total mass of the system equals mass A plus mass B, and the total mass of the system is 20 kilograms. I want to find mass A, and I know that mass B is 5. When I solve for mass A, I'll find it's 15 kilograms. I'll go ahead and write that in now. I know it's 15. So 15 plus 5 is 20. Okay, now, the next question is, what is the net force acting on object B? Well, the sum of the forces equals mass times acceleration. And I know that the mass is 5 kilograms and the acceleration is 2.5. So therefore, 5 times 2.5 gives me 12.5 newtons. 12.5 newtons is the net force acting on object B. And that's in the direction that we decided is positive. That's the downward direction. What is the magnitude of tension force T2? In this case, I'm going to say the sum of the forces is going to equal the downward force plus the upward force. The downward force, mg, is 50 newtons. And I'm looking for T2, but I know that the net force on that object is 12.5 newtons. So 12.5, the net force acting on the system, which I got by multiplying mass times acceleration, equals 50 down plus T2, which is up, which is going to be, it should be a negative value. When I substitute in 12.550 and T2 and solve for T2, I find that I get negative 37.5, which makes sense for it to be negative because it's going the opposite direction from what we're calling positive. But I was asked what the magnitude is, so it's 37.5 newtons. Now 4. Oh no, we're introducing friction to all of this. Oh, Samson, must you? I must. So, I have two masses on a string. I assume that the pulley is both, that string are massless. The pulley is frictionless, but there is friction acting between the table and object A, and that the coefficient of friction is 0.3. So the first thing I need to do is I need to figure out what is the amount of friction acting on this object here. So we can tell, just from looking at this, that the motion is going to be downwards. So friction is going to act this way. So what I need to do is I say, well, the force of friction equals mu, which is 0.3, times the normal force. Now since mg downwards is going to be, mg is going to give me 60, the normal force must also be 60 since this is horizontal. So I'm going to plug in 60 newtons here for the normal force, 0.3 here. That gives me 18 newtons of friction force. So the friction force is going to be 18 newtons. What is the net force acting on the system? Well, in this case, I don't know how fast the system is accelerating, so I'm going to have to approach it by adding up the forces. So the sum of the forces is going to equal mg pulling down and friction pulling the other way. So it's going to be mg plus friction. Mg is 50 and friction is negative 18. That gives me 32 newtons is the net force acting on the system. What is the acceleration of the system? Well, to find the acceleration equals the net force divided by the mass. The net force we found to be 32. The mass of the system is 5 plus 6. It's 11 kilograms. So 32 divided by 11 gives me 2.9 meters per second squared is how fast it's accelerating downwards. How long will it take it to reach the floor? That's a kinematics question. So I'm going to, since it's accelerating at this rate, I can use d equals 1/2 a t squared. So 2 equals 1/2 of 2.9 times t squared. And when I solve that for t, I'll get 1.7 seconds. I'm sorry, 1.17 seconds. Now, what is the magnitude of the tension force T1? So, what is this tension force here? Alright, now we're going to keep in mind there is friction here, so that's going to make it a little bit trickier. So, what I'm going to go with is this. The sum of the forces acting on a system is equal to the mass of the system times the acceleration. Since the mass is 6 and the acceleration is 2.9, I know that the sum of the forces acting on the system must be 6 times 2.9, or 17.4 newtons. Now that I know what the sum of the forces is, I can say, well, the sum of the forces is also equal to the sum of the forces. What are the forces acting on it? Well, I'm going to ignore these two because they cancel out. So the mg and normal cancel each other out. They're 0. So that leaves me with, I have the tension force acting this way and friction acting this way. So the sum of forces on this is going to equal T1 plus F2. I'm sorry, plus force friction. So I'm going to substitute in. I've already determined that the net force acting on the system is 17.4. I don't know what T1 is, but I do know that if I add it to force of friction, which is negative 18, what I'll get is T1 equals 35.4 newtons. Oh, it's just getting worse, isn't it? Look at this one. But it's beautiful. Come on, you can do this. You know you can. All you have to remember is the sum of the forces equals mass times acceleration. Well, in this case, let's just look here. What we've got is a situation where we've got 100 newtons of gravitational force pulling the system in this direction. And now I'm told that there is friction between the surface and these objects, and the coefficient of friction is 0.2. So I'm going to start off by figuring out what is the friction acting on each of these objects. So the friction acting on object A is going to be equal to mg down equals normal up, so that's 60. 60 times mu, which is 0.2, gives me 12 newtons of friction force acting here. And here I have 40 is my normal force, times 0.2 gives me 8 newtons of friction force. So the total amount of friction force is 12 plus 8. I have a total friction force acting this way of 20 newtons total. Because what I have here is 12, and what I have here is 8. So let's just add this all up to find my net force. What is the net force acting on the system? Well, it's going to be mg plus the force of friction acting on object A plus the force of friction acting on object B. mg is 100, which is 10 times 10, plus negative 12 plus negative 8 gives me a grand total of 80 newtons is the net force on the system. Therefore, I can calculate the acceleration of the system, because the acceleration is always equal to the net force divided by the mass. The net force in this case is 80 newtons, when we take into account friction, divided by the mass of the system, which is 10 plus 4 plus 6, which is 20. 80 divided by 20 gives me 4 meters per second squared of acceleration. So what is the magnitude of each of the following forces? T3, T2, T1. Okay, so let's start off with T3. T3, if I want to find that, what I have to say is, well, the sum of the forces acting on this is going to equal to its mass times its acceleration. So the mass is 10, and the acceleration is 4, so the sum of the force acting on it equals 40 newtons. If the sum is 40, and there's two forces acting on it, mg down and T3 up, I think we can figure out what they are. So I'm going to say 40 newtons is the sum of the forces equals mg pulling down and T3 pulling up, and when I solve it for T3, I'll get negative 60 newtons. Well, T2 is going to be the same thing, except instead of pulling this way, it's pulling this way, so I can put 60 newtons there for T2. I don't even have to do any math. I could if I want to, but I'm not gonna. And now I'm going to go to T1. To find T1, I have to do the same process over again. I'm going to say, well, the sum of the forces equals mass times acceleration. Mass is 6, acceleration is 4, so if I say 6 times 4, I get an acceleration of 24 newtons. That is what the sum of the forces equals, mass times acceleration. The sum of the forces also equals all the forces added together. Now, again, the gravitational force and the normal force acting on this object cancel out, leaving me with two forces, T1 and friction. So the sum of the forces equals T1 plus friction. The sum of the forces I've calculated to be 24 newtons. I'm looking for T1. Friction is negative 12. 24 minus negative 12 is going to give me positive 36 newtons. And if you get confused, this negative sometimes can be a problem. Think of it like a tug of war. clearly this must be tugging harder than this in order for it to work, because otherwise it wouldn't move this way. T1 is winning, and friction is losing. If friction is pulling this hard, T1 must be pulling hard enough to make this accelerated at 4. So the answer is 36. Let's keep going here. The diagram above shows two masses connected by a string. Assume that both the pulley and the string are massless, and the table and the pulley are both frictionless. Well, that's nice. The trick here is I wasn't told the mass of the object A, but I was told what its weight is. Its weight is 40 newtons. So if mg equals 40 newtons downwards, it's pretty easy to figure out that m times g, which is 10, equals 40, so therefore m must be 4. I have a 4 kilogram mass here. I'm just going to write that in. So, how fast would the system be accelerating? Well, acceleration, as always, equals the sum of the forces divided by mass. Since this is frictionless, it's not contributing any force to the system, just mass to the system. So here's the only force causing the system to accelerate, mg, which is 60 newtons. And I have to divide that by the mass of the system, which is 6 plus 4 is 10. The system is accelerating at 6 meters per second squared. If the entire system was now in an elevator, you gotta be kidding me. No, you didn't do this, Eric. So I put the whole darn thing in an elevator, and the elevator is accelerating up at 2 meters per second squared. How fast would object A accelerate in this case? How fast would it accelerate towards the pulley? Now, you know what? There's lots of ways of approaching this. Here's how I approach it. I'm going to say, you know what? The force acting on this is equal to mass times acceleration. Now think of it this way. If I cut this string and just let this object fall, and the elevator was parked, how fast would it accelerate to the floor? Well, it accelerate to the floor at 10 meters per second squared. Now, the floor of the elevator is accelerating upwards at 2 meters per second squared. So in that case, if I was in the elevator and cut the string and watch it fall, I would see it approach the floor at 12 meters per second squared. I'd see it approach at g plus 2. So I'm going to solve it this way. I'm going to say the force acting on it is going to, the force acting on this one is going to equal mass times, instead of g, I'm going to use 12, which gives, and you know what, Mr. Sampson, that does not equal 720 newtons. What the heck are you thinking? It doesn't equal that at all. What it equals is 72 newtons. Good golly. So now let's answer the question. How fast would object A accelerate towards the pulley? Well, the whole system is going to be accelerating at the same rate, so I'm just going to calculate that. The acceleration of the system equals the net force on the system divided by the mass of the system. This is not the net force on the system. I think it's actually 72 newtons divided by 10 kilograms is going to give me 7.2 meters per second squared, which makes sense. It's a little bit faster than it was if it wasn't in an elevator moving upwards. Gosh, why did I ask that one? Because it's a cool question, that's why. Well, the fun never stops, does it? So now I've got two objects that are hanging on a pulley like this, but instead of having a flat surface, I have an inclined surface. That's fair enough. It's just going to change what happens here. This is going to contribute more than just mass to the system. It's going to contribute some force to the system. So for right now, at least we've got this going for us. The ramp surface is frictionless. Okay, we got that going for us. So object A has a mass of 3 kilograms. So I'm just going to write that in here, 3. And object B has a mass of 7 kilograms. So if I want to find the net force acting on the system, what I find is that mg is 70. Now I've got to figure out what is the downward component here caused by this 3 kilogram mass. So I'm going to say the force of gravity acting on A equals mg sine theta, because remember this component is always equal to the sine of the mg. So this is 3 kilograms times gravity, mg is 30, times sine of 30 gives me 15 newtons. So I have 15 newtons acting in this direction. I have 70 newtons acting in this direction. So if I want to find the net force acting on the system, the net force equals the sum of the forces. So the force acting on A, here's what I'm going to say. I can tell that this object is going to be moving in this direction, so I'm going to make this be positive, and I'm going to make this one be negative. because they're pulling in opposite directions. So I'm going to say the net force is going to be negative 15 plus 70 gives me 55 newtons. So this is what I'm going to call the positive direction, and it's 55 newtons. So how fast and which way does object B accelerate? Well, it accelerates as fast as the system accelerates. So the acceleration of the system equals the net force of the system divided by the mass of the system. Are you starting to notice this is a pretty common theme here, isn't it? The net force on the system we have calculated to be 55 newtons. The net mass of the system is 7 plus 3 is 10. So the system is going to accelerate at 5.5 meters per second. So therefore both A and B will accelerate at 5.5 meters per second. Now let's take this next question. How fast and which way would object B accelerate if we switch them around? So now I'm going to put object B over here, I'm going to put object A over here. Alright, so now what I've got is, let's see, I drew it down here. So now what I've got is object A is pulling down with mg, which is 30, and I have object B is over here, and it's pulling down at mg sine theta. So 70, which is mg times sine of 30, is 35 newtons. So I'm going to put 35 newtons pulling this way and 30 newtons pulling this way. So the sum of the forces is going to equal 35, which I'm going to make positive because it's larger, and therefore the motion is going to be in this direction, minus 30 this way gives me 5 newtons in this direction. So how fast will it accelerate? It's going to accelerate as fast as the system goes. So it's going to be acceleration equals the sum of the forces divided by the mass. The sum of the forces in this case is only 5 newtons. The mass, once again, is 7 plus 3. Well, I guess I should say 7 plus 3, which is 10 kilograms, which gives me 0.5 meters per second squared. Okay, here goes our very last one. Oh boy, this time we got incline and friction. Once you've gotten to this point here, you are just awesome. So here we go. In this case, we have object A has a mass of 10 kilograms. Object B has a mass of 5 kilograms. And the surface, which is inclined at 50 degrees, does have friction, and the coefficient of friction is 0.25. So the first thing I'm going to do is I'm going to figure out what are the forces acting on it. So if I'm going to find the net force, I need to find all the forces. Well, if this is 5, then mg down is 50. Now I have to find what the gravitational component of A's mass is. So here I have 10 kilograms, so mg is 100. So mg sine theta is going to give me this. mg is 100. Sine theta of 50 when multiplied by 100 gives me 76.6 newtons in this direction. So it's pulled down at 50 this way, 76.6 this way, but wait, there's also friction acting here. So the way I find friction is, I remember that the force of friction equals mu times the force normal. The force normal is going to be found by multiplying mg times the cosine of theta. So when I say mg cosine of theta, I'll get 64.3. 64, so 100 times cosine theta gives me 64.3. Mu is 0.25, so I get 16 newtons of friction force. Friction force is going to act against the motion. So let's pretend for the second that there is no friction. Which way would the system move? 50 this way, 76 this way. The system is going to slide this way. Well, since it's sliding this way and there is friction, the friction always acts against motion. So I have 16 newtons in this direction. So now let's find the net force acting on the system. The net force equals the sum of all the forces acting on it. I have 76.6 this way, which we're going to call positive since it's the direction of motion, plus negative 50 since it's acting against motion, plus negative 16 since it's acting against motion. Add those all up, and what you get is 10.6 newtons is the net force acting on this system. And it's going to cause it to accelerate at what rate? Well, the acceleration of the system equals the net force of the system divided by the mass of the system. The net force of the system is 10.6 newtons. The mass is 5 plus 10, which is 15, so it's accelerating at 0.71 meters per second squared and A is accelerating in the downward direction. Hey, look at that. We're done with our homework. I hope you enjoyed it as much as I did, and I hope you were successful. And if not, please come see me and get help. This is a big part of physics. These Atwood machines really get to the heart of, do you understand forces and accelerations and Newton's second law and all that stuff. So they get used a lot to see how students are doing when it comes to understanding forces.